A strand of glass, no thicker than a hair, rests on the ocean floor, subjected to 400 atmospheres of pressure. Through it moves the modern world. 99% of all intercontinental data travels not through satellites or the air, but through fiber optic cables resting on the seabed. Over 1.48 million kilometers of them are threaded across every ocean basin on Earth through more than 600 active and planned systems. These cables fail roughly 200 times a year. When they do, entire nations lose contact with the outside world. Restoring them requires one of the most specialized engineering operations on Earth: surgery in pitch black, under crushing pressure, on a target thinner than a garden hose, at a depth where a single misstep can disconnect a continent. This is what that system looks like, what breaks it, and what it costs to fix. The core of every subsea cable is an optical fiber, a thread of silica glass, classified as G654 single mode and optimized for undersea transmission. Light enters one end and travels vast distances, but not without cost. With every kilometer, a fraction of the signal is absorbed or scattered. Engineers call this attenuation, and in modern submarine fiber, the rate sits between 0.15 and 0.17 decibels per kilometer. That sounds small, but compounded across an ocean, the signal would vanish entirely without intervention. So every 50 to 100 kilometers along the cable, there is a repeater, an amplifier, sealed inside a pressure-hardened housing, powered by up to 20,000 volts of direct current fed through the cable itself. The ocean acts as the electrical ground to complete the circuit. This means a cable crossing the Atlantic is not just a passive strand of glass. It acts as an actively powered system, with dozens of amplification stations strung along the seabed like beads on a wire. To squeeze more data through each fiber, engineers use a technique called dense wavelength division multiplexing, which we'll refer to as DWDM. Multiple streams of data, each carried on a slightly different wavelength of light, travel simultaneously through the same strand. It's the optical equivalent of sending dozens of radio stations through a single antenna, each tuned to its own frequency. Newer systems are pushing further with space division multiplexing, which increases the number of fiber pairs inside a single cable, sometimes to 24 or more, to meet the bandwidth demands of artificial intelligence infrastructure. But the glass is only the beginning of the problem. Because that fiber must survive on the ocean floor for 25 years without maintenance. The cable that protects it is not a simple tube. It is a composite of 8 distinct layers, each solving a different engineering problem. At the center, the optical core. Around it is an aluminum or copper tube that acts as both a power conductor and a water barrier. The voids are filled with petroleum or silicone jelly to prevent air pockets from compressing under pressure. Stranded steel wires provide tensile strength. Polyethylene insulation, which is a type of plastic, prevents electrical leakage into the sea. A polycarbonate jacket adds rigidity. Galvanized steel armor resists anchors and fishing nets, and the outer wrap of polyethylene or bitumen protects against corrosion and abrasion. Near the coast, the cable can be 50 millimeters thick, double-armored, with a braking load exceeding 700 kilonewtons. That is strong enough to resist a ship's anchor dragging across the seabed. But in the deepest ocean, where human activity is rare, the cable thins to as little as 12 millimeters. The thinnest, most vulnerable sections of the cable sit in the safest places, the deep abyssal plains where no trawler or anchor will ever reach. And the thickest, most armored sections guard the most dangerous stretches, the shallow waters near shore, where nearly all the damage occurs. About 200 cable faults occur every year worldwide, and the cause is not what most people expect. It is not the ocean itself. It is us. Data reveals that roughly 86% of all cable faults are caused by human activity. Bottom trawling fishing nets account for 28%. Ship anchors dragging across the seabed cause another 14%. And a further 44% are attributed to unspecified human activity, suspected fishing, or anchoring where confirmation was not possible. Geological events, such as earthquakes, landslides, or turbidity currents, account for just 7%. Abrasion from currents, 4%. Internal equipment failure, 3%. The geography of these faults follows a clear pattern. 44% of repairs happen in territorial waters, within 12 nautical miles of shore. Another 54% occur in the exclusive economic zone, within 200 nautical miles. Only 2% of faults happen on the high seas. The deep ocean is, statistically, the safest place for a cable to be. But when geology does strike, the consequences can be catastrophic. On December 26, 2006, a magnitude 7.1 earthquake hit off the southwest coast of Taiwan. The tremor itself was not what severed the cables. It triggered a cascade of submarine landslides that evolved into turbidity currents, fast-moving rivers of sediment that tore across the ocean floor. Engineers reconstructed the event forensically using the precise timing of each cable break. The first cable snapped within a minute of the earthquake near the epicenter. 5 minutes later, a second cable failed 30 kilometers downstream. 4 hours later, another at 110 kilometers. 9 hours after the quake, a cable broke 173 kilometers away. By mapping distance against time, investigators calculated the speed of the turbidity current. Near the epicenter, it was moving at roughly 20 meters per second, 72 kilometers per hour. As it spread across the abyssal plain, it gradually slowed, but even at the farthest breaks, the current averaged around 20 kilometers per hour. It took 11 ships and 49 days to restore normal telecommunications service to Southeast Asia. The 2006 event was severe. However, it wasn't the most catastrophic event. On January 15, 2026, the Tonga Ha'apai volcano erupted in the South Pacific. The blast produced a tsunami and atmospheric shock waves felt around the planet. But for Tonga, the most devastating consequence was invisible, an underwater sediment flow that sliced the nation's only international cable in 2 places. Forensic surveys of the seafloor afterward revealed that the volcanic debris flow reached speeds between 68 and 122 kilometers per hour. It was the fastest underwater current ever documented. The flow carved scours more than 100 meters deep into the seabed and buried sections of Tonga's domestic cable under 20 meters of volcanic material. Tonga's connection to the global internet depended on a single $32 million cable link through Fiji. 1 cable, 1 route. When it broke, 100,000 residents lost all digital connectivity for 5 weeks. This structure is the architecture of a single point of failure, and it is not unique to Tonga. The world's data does not flow evenly across the ocean floor. It funnels through a small number of geographic choke points, and the most critical of these is Egypt. Approximately 17% of all global internet traffic and nearly 100% of data flowing between Europe and Asia pass through the Red Sea and across a narrow terrestrial corridor between the Red Sea and the Mediterranean. The cables do not route through the Suez Canal. The risk of anchor strikes in that confined channel is too high. The grounding of the Ever Given in 2021 demonstrated just how vulnerable that corridor is to a single vessel. Instead, the cables converge in a parallel terrestrial crossing so tight that redundancy is limited. In March 2024, a single event severed 4 cables in the Red Sea. The disruption affected an estimated 25% of telecommunications traffic between Asia, Europe, and Africa. The Luzon Strait, between Taiwan and the Philippines, sits directly above the same seismically active submarine landslide zone that produced the 2006 disaster. The Strait of Malacca funnels Southeast Asian connectivity through waters congested with shipping. The Strait of Hormuz carries Gulf connectivity through waters defined by geopolitical tension. Each of these corridors is a bottleneck, and each represents a place where the physical internet is concentrated into a thin, targetable line. When a cable does break, what follows is one of the most specialized engineering operations on Earth. It is surgery, performed in the dark, under crushing pressure, on a patient thinner than a garden hose, at a depth where a single misstep can sever a continent's connection to the world. The operation begins at the landing station on shore. Engineers use a diagnostic tool called Optical Time Domain Reflectometry, or OTDR. The principle is straightforward. A laser pulse is fired into the cable. As it travels, the glass fiber scatters a tiny fraction of that light back toward the source. When the pulse reaches the break, the backscatter signature changes abruptly. Because the speed of light in silica glass is known, the time delay tells engineers exactly how far away the fault is, to within meters, across thousands of kilometers of cable. Once the breakpoint is identified, a cable ship is mobilized. These are not ordinary vessels. They are floating factories, purpose-built for deep ocean repair. One of the most advanced is Le Pierre de Fermat, operated by Orange Marine. It is equipped with dynamic positioning systems that hold the ship perfectly stationary in rough seas. No anchor, no drift. Below decks, climate-controlled jointing rooms provide the sterile environment required for the most delicate phase of the repair. And in the hold, the ship can carry up to 9,000 kilometers of spare cable coiled and ready for deployment. The ship carries one other critical piece of equipment, a linear cable engine. This is the machine that controls the tension on the cable as it is lowered or recovered through several kilometers of water column. If the tension is miscalculated, too much or too little, the cable will snap or kink. And a kink in a fiber optic cable is irreversible damage to the glass inside. The entire repair depends on managing this load. When the ship reaches the fault coordinates, the first task is to find and isolate the damaged ends. In deep water, below 2,000 meters, a remotely operated vehicle, an ROV, is deployed. The ROV descends to the cable, inspects the damage, and makes a clean cut on either side of the fault. In shallower water, the ship may instead drag a cutting grapnel along the seabed, perpendicular to the cable's path. The grapnel is designed to hook the cable and sever it at a controlled point. Now, the repair enters its most painstaking phase. The first end of the cable is recovered to the deck using the linear cable engine. This end is tested to confirm it is still electrically and optically connected to the landing station on shore. If the connection holds, the end is sealed, attached to a surface buoy, and lowered back into the water. The buoy marks its position for later retrieval. The ship then repositions to recover the second end. This is brought aboard and taken into the jointing room. Inside that room, technicians perform a fusion splice. The silica strands of the old cable and a fresh section of replacement cable are aligned under a microscope and bonded at the molecular level using an electric arc. The precision is extreme. Any misalignment, any contamination, any impurity at the junction will degrade the signal across the entire link. This is the moment the repair either works or doesn't. The completed splice is sealed inside a joint body, a protective housing engineered to withstand hydrostatic pressures exceeding 100 megapascals. At 4,000 meters, the pressure on that joint is roughly 400 times what we feel at sea level. With the second end spliced to the new cable section, the ship begins paying out the replacement cable as it navigates back toward the buoy. The cable feeds over the stern through the linear cable engine, descending through the water column to the seabed below. The ship must maintain a precise speed and course to ensure the cable lies flat and does not pile up or stretch. When the ship reaches the buoy, the first end is recovered to the deck for the final time. The last splice is completed. The joint body is sealed. Now comes the lowering. The repaired section must be returned to the seabed without damage. An acoustic release mechanism is used, a hook that opens in response to an ultrasound ping transmitted from the surface. The cable descends on its own weight, guided to the seabed. In many cases, the repair is not finished yet. An ROV is redeployed to the seabed, this time carrying high-pressure water jets. The jets carve a trench in the sediment, and the cable drops into it, buried beneath the sea floor. This is the final layer of defense against the fishing nets and anchors that cause the vast majority of faults in the first place. The entire operation, from fault detection to reburial, can take days to weeks, depending on weather, depth, and the severity of the damage. A typical fiber optic repair costs between $500,000 and $1.5 million. Power cable repairs, which involve far heavier and more complex materials, can exceed $50 million. And globally, this happens 200 times a year. The pattern of vulnerability has not gone unnoticed, and the response is reshaping who owns the ocean floor. For decades, subsea cables were built and operated by telecommunications consortia, groups of national carriers sharing the cost and capacity of a system. But in recent years, a different class of player has moved in. The hyperscalers, Meta, Google, Amazon, and Microsoft have shifted from being customers of cable systems to becoming the primary investors and operators. These companies now represent roughly 50% of the overall market for subsea cable investment. The reason is control. When your business depends on moving massive volumes of data between continents, for cloud computing, for AI model training, for billions of users, you cannot afford to be a tenant on someone else's infrastructure. The most ambitious example of this shift is Meta's Project Waterworth. It is a single cable system spanning 50,000 kilometers, designed to connect 5 continents. If completed, it will be the longest privately owned cable in history, to be a tenant on someone else's infrastructure. But Waterworth is not just about length. Its route is a deliberate exercise in geopolitical engineering. The cable is designed to run through deeper water, up to 7,000 meters, and to intentionally avoid the highest-risk choke points. It does not pass through the Red Sea. It does not cross the South China Sea. The strategy is sovereignty through routing. Build a path that cannot be easily severed by regional conflict, geological hazard, or the concentrated vulnerability of legacy corridors. At the same time, the cables themselves are being reimagined. The Science Monitoring and Reliable Telecommunications Initiative, SMART, aims to turn passive data cables into active environmental sensors. The plan is to equip every optical repeater with instruments that measure temperature, pressure, and seismic acceleration. A cable crossing an ocean basin would become, simultaneously, a data highway and a continent-spanning seismometer. One proposed system would connect Antarctica, currently the only continent without a subsea fiber link, to the global network, providing 1 to 10 terabits per second of bandwidth while monitoring the Southern Ocean in real time. The system would use distributed acoustic sensing, a technology in which shore-based lasers detect tiny vibrations in the fiber itself, turning the entire cable into a continuous listening device capable of tracking tectonic shifts, ship movements, and marine life across thousands of kilometers. Antarctica's dependence on low-bandwidth satellites currently limits the data that researchers can transmit from the continent. A smart cable would change that and, in the process, transform the infrastructure from a vulnerability into a scientific instrument. But all of this, the hyperscaler investment, the route diversification, and the sensor integration, is a response to a deeper truth that the evidence makes plain. The global internet is not a cloud, it is not distributed, it is not resilient in the way most people imagine. It is a physical network of glass and steel threaded through the most hostile environment on Earth, protected by a few centimeters of polyethylene, powered by voltages that would kill on contact, and maintained by a small fleet of specialized ships that are themselves aging and insufficient in number. 200 faults a year, 86% caused by fishing nets and ship anchors. Chokepoints where 17% of the world's data passes through a single corridor. Nations left offline for weeks by a single cable cut. It works remarkably well, carrying petabits of data across oceans with latencies under 100 milliseconds. But it works because it was engineered to, not because it is invulnerable. In the 1850s, the first transatlantic telegraph cables were insulated with gutta percha, a natural latex that degraded in seawater and failed within months. Today, the cables that carry 99% of the world's intercontinental data are engineered for a 25-year lifespan, armored in galvanized steel, powered at 20,000 volts, and amplified every 50 to 100 kilometers by repeaters sealed against pressures of 37 megapascals and beyond. The material has changed. The vulnerability has not. The Internet's deepest foundation is not a server farm, nor is it a satellite constellation. It is a thread of glass on the ocean floor, no thicker than a hair, carrying the weight of modern civilization through the dark. And it is only as strong as the few centimeters of steel and polyethylene that stand between it and the sea. If the systems hidden beneath the ocean's surface held your attention, there is another, one that carries not data but heat. And the evidence says it is failing. That story is here,